All right, before you get your hands dirty with the actual mechanics of probability functions, we need to pop the hood and look at the engine underneath. Today, we're entirely stripping away the syntax, the code, the paint job, all of it. This explainer is all about orienting your mind to the raw, conceptual machinery before you dive into the real work.
To really understand this machinery, let's ground it in some reality. Imagine you manage this bustling waterfront market, and you desperately need to answer a seemingly simple question. How many stalls does a typical visitor actually stop at? Well, there's a problem. A massive gust of wind just blew every single one of your historical visitor records right into the lake. Gone. Or picture an ER evaluating its pricing against inflation. They're staring at a $3,000 patient bill and asking themselves, just how extreme is this compared to our normal charges? These are the kinds of real-world engineering and business problems that desperately demand answers, even when your data is chaotic or, literally underwater.
Quick caveat before we go any further, the conceptual logic we are unpacking here applies identically across both R and Python. It doesn't matter which environment you're working in, the foundational engine behaves the exact same way. So consider the rest of this a completely syntax-free space.
So, what actually is a probability function? It's definitely not just some isolated equation you memorize for an exam. Think of it as a mathematical translation device. It takes a raw, messy distribution, like that stack of hospital bills or a tally of market stalls, and it physically translates that shape into exact, actionable answers.
And that translation device essentially exists to answer four universal questions. 1. How dense is this specific value? 2. How much of the total distribution lies at or below it? 3. What exact value sits at a given percentile? And 4. How do we draw a simulated sample from it? The absolute beauty of this system is that these four questions exist for every single named distribution out there, in this exact order with the exact same meanings. Learn them once, and you literally have them all.
But what happens when reality hits and you just cannot observe the entire population? Think back to our waterfront market. You might only have a fact or two remaining. Say, you remember the median was around 5 visits, and obviously a visitor can't make negative visits. Well, here is the brilliance of this machinery. If you can name a plausible family for that distribution based on those surviving facts, you can construct an unobserved probability function. You can start answering precise questions about data you never even managed to collect.
Now, if you do have the data, you can actually estimate a density curve directly from the values themselves, effortlessly filling in the gaps. Think about it. If you observed an ER bill of $1,493 and another at $1,500, the probability of the numbers between them should be pretty similar, right? By estimating this, the data itself becomes an equation. It transforms from this static, historical list of numbers into a continuous, flowing mathematical curve.
So, returning to our hospital bill scenario, how extreme really is $3,000 compared to the norm? This brings us directly to the concept of the p-value. In this context, a p-value is simply a cumulative probability. That's it. It is the exact share of the distribution that is more extreme than what you just observed. It's a physical measurement of extremity, a literal area under a curve. It is not some final, definitive verdict on reality.
And this brings us to the most critical conceptual mistake people make in this space, the probability density function and the cumulative distribution function. They are not two separate objects that you need to memorize independently. They are intimately connected. One is simply the running total of the other. The exact same cumulative probability that you'd represent as a shaded area under one curve is just read as a simple vertical height on the other. The specific question you were trying to answer is what dictates which view you reach for.
So, how do you know if you're conceptually on the right track? Well, a sensible result means the components logically align. The area you calculate mathematically perfectly matches that cumulative height. A suspicious result, on the other hand, happens when your calculated values fundamentally rebel against the question you asked. If you need a cumulative probability for an at-most question, but you generate a relative frequency that isn't bounded between 0 and 1, yeah, your math is sounding a massive alarm.
Look, reaching for a density function when your question actually demands a cumulative probability is, hands down, the easiest way to fail silently. The numbers will often look just plausible enough to go entirely unnoticed, so before you execute your next function, you have to stop and ask yourself, are you actually answering the question, or are you just failing silently?